How's my font size? Is that good? Yeah? Got just another minute. How's that font size? Is that good? Like bigger chalk. See if it's like a constant mental reminder. Okay, I'm going to start. So welcome back to Underactuated. Today I want to talk about nonlinear dynamics. It turns out that nonlinear systems do a whole bunch of kooky things that linear systems never do, and they actually change the way you should program your robots. So I need to spend a little time today just making sure people have the basic definitions and also intuition about what nonlinear systems can do and how we go about, bending them to our will gently. So, like I said, some definitions, and there's a particular, I think, very powerful and great way to think about nonlinear systems when they're low dimensional. We can draw a lot of pictures and understand what they're capable of. Okay, so, my goal is to make you love dynamics. I don't know if we get there today, but maybe by the end of the term. Let's start with, I told you we were going to use a lot of very simple pendula kind of systems, and we're going to do that exactly today. Let me start with the simplest of all, which is a single pendulum. And I always use the term simple pendulum. Where simple sort of implies point masses. That's not a hard, fast rule, but I just have I'm going to take a massless rod and put a point mass on the end of it. I've got a length L. The coordinate I'll call theta. Gravity's pointing down, okay? Again, the equations of motion for this are there's just a recipe you can run through. In this case, it's just the kinetic energy is 1/2 ml squared theta dot squared. That's what the velocity of this point is. The total potential energy is just mg L cosine theta. Negative, I guess, the way I've drawn it. And if I turn through my Lagrangian, then the thing that comes out is ml squared theta double dot, we're going to see this one a lot here, plus mgl sine theta equals q, is sort of the standard dynamics text term for, this is some generalized force. So why generalized? It's not necessarily a Cartesian force. This is the force in the coordinate, in this case, of theta. So in this case, it's the torque. Wow. So we get to apply a torque there. Okay. In particular, there's two types of torque that we're going to add to this. We're thinking about adding to this system. They don't come, it doesn't come directly out of this Lagrangian, but we're going to put in friction. So we're going to say that for us, Q is going to be some friction damping term. And then I'm going to have a control input, a motor torque that I can apply to. So tau, or I'll just start using U here because we think of U as our input. So that gets us to, if I move the damping over here, then it looks like a standard second order spring damper kind of equations. These are our pendulum equations to know and love. Okay, so that's just a differential equation, right? This is the stuff of MIT 1803 or whatever undergraduate differential equations course you've taken. So the standard recipe, if you're given a differential equation, would be, I'd say, given theta of 0 and theta dot of 0, those would be my initial conditions. Oh, good, thank you. I put a box around it, I gotta have it right. So given my initial conditions, then it seems like a reasonable question in a differential equations class to say, you tell me what is theta of t? That's the standard stuff of differential equations, right? Okay, so here we go. So first we can start with theta dot of t is theta dot 0 plus an integral from 0 to t of my theta double dot dt. This is just my ml squared. Okay, but this is sort of a tease because I actually can't get to the next line. It's not that I'm not good at calculus, but it's actually, there's no good solutions to this problem, okay? So the things, the standard fare of differential equations, you just tell me how the system evolves with time. I didn't have to do much. This is almost the kind of equations you see in a differential equations course, but as soon as I put in this sign, I actually can't integrate it in the sense that even when b equals 0, okay, that's like the simplest case. There's a famous solution to that. It's an elliptic integral of the first kind. So there's an answer that has like a, in an elementary terms, but as soon as I put b not equal to 0, I don't even have that. I can't give you a closed form solution to theta t that is satisfactory in any way. Certainly, if it's going to be dependent on my control input, it's dead. So that's a little terrifying, right? So one of the amazing things about linear systems and linear differential equations is I can solve them. I can tell you how x is going to evolve for all time. And we're in a new world here of nonlinear differential equations where you don't get to answer that question. There's no satisfying answers to that question. So we don't have to pack up and go home. There are other questions you can ask. But you have to realize that the questions, you have to be more clever to solve some basic problems, okay? For instance, I think you know relatively a lot about pendula. I don't know if you have one at home, but you have some intuition. I think if I asked you for this system that's got let's say that my torque command is 0. So I've just turned it off. I'm going to let it go. Let's say my damping is positive and this B is positive, which means I've got real damping. Then if I ask you, what is theta infinity, right? The limit as t goes to infinity of theta t. Right? We have some intuition about that. That's satisfying. At least I can talk about the long-term solution of the system. That's a start. There are other questions you could ask that are pretty reasonable, like, will it ever do something bad? I mean, for instance, if let's say it's not a pendulum, but it's a drone or an autonomous vehicle that's moving around at high speeds, and you just want to ask, is it ever going to hit a tree, right? Is it ever going to go into a region that's not ideal? There are questions like that you can ask without actually solving the differential equation, right? Will it ever enter a safe set or a bad set? For instance, just to get you thinking, right? So how could I say something like that about the pendulum without knowing how to solve the differential equation? Well, if u is 0, so I've got no extra input, and I start with in some initial condition, I've got damping, then I'm not only do I know at time goes to infinity, I'm going to be here, you can also say with a lot of confidence that you're never going to be here, right? The energy on the system never went up. So the sub-level set of states for which the energy is at my initial energy or below is a invariant set. There's a set of states that I will never leave, okay? So I can say safely, I will never hit a tree, right, with my pendulum. I did hit a tree with a pendulum once, but that had energy going in. Okay, so it's a new world of sort of these nonlinear systems, and we need new tools to think about them. And we'll talk about Lyapunov analysis. We'll use lots of optimization and optimal control to think about them. And there's ways to solve these problems without solving that explicitly. But the reason we can't solve this explicitly is because theta t can do crazy things, both in time and in state and in other things. And we're going to get our head around that with this idea of using graphical analysis. So there's a great book on graphical, thinking about nonlinear systems, written by Steve Strogatz. Highly recommended. I put a picture here too in case that's too small. I'm going to sort of try to channel Steve Strogatz just for the hour here to give you a sense of the kind of ways you can think about some of these systems very graphically. Okay, so we'll start by doing graphical analysis of the simple pendulum. And actually, I want to start even simpler, okay? I want to do the overdamped pendulum. Okay. So intuitively, I want B to be very large because I claim that that's going to simplify my dynamics. Okay. So, but let's be a little precise about this because I want you to be good dynamicists. So, what does it mean to say B is large, or what do I really want? Right. I'd like this term to be bigger than this term, sufficiently bigger than this term that I can effectively think about the system as a first order set of equations because the contribution here is small, okay? So, I'd like to say something like B is a lot greater than ML squared or something like that. But don't say that because that sort of doesn't parse. Right. Somehow what I want is B theta dot, which is in the units of kilograms meters per second squared. And this thing, which is also in the right units, to be related for some reasonable set of, some characteristic set of theta dot, theta double dot, right? So somehow over the set of thetas that I care about and theta dots I care about, I'd like that term to be bigger than this term. So the way you think about that in dynamics is you try to do dimensional analysis. You think about what's a characteristic. In this case, the thing that's missing between the units is a time constant. So you take a characteristic time constant. Let me just say that more carefully here. So what units are ml squared in? That's obviously kilograms meters squared. The units of B are actually kilograms per meters squared over seconds. It's kind of a weird one, but that's what it is. Okay. So in order to compare those two, I need to get a factor of 1 over second to put them in the same units. What's a characteristic time constant for a pendulum would be its natural frequency. Okay? So the natural frequency of the pendulum square root of g over L has units 1 over seconds. So what I'm perfectly happy to say, and sort of is a meaningful thing to say now, is that B, I need to get the opposite of that. So B times square root of L over G is bigger than ml squared. That's just a taste of dimensional analysis, okay? And people who think a lot about dynamics often do this very well. For complicated, for fluid systems, other things, you can compare different systems, simplify them by making these arguments as long as you get your units right. Okay, so my claim is that if this is true, then in the cases I'm worried about, of sort of nominal characteristic oscillations of the pendulum, that this term is going to be much bigger than this term. So I can make a reasonable approximation of my dynamics as B dot equals now just U minus MGL sine theta. So the dynamics become first order. I've lost my second derivative, okay? What does that mean physically? This is like I say, the overdamped case. This is the case where the pendulum's operating in molasses or something, right? It's like the low Reynolds number case if you're into fluids, right? This is where everything gets simpler because inertia doesn't really matter. Accelerations don't matter. And it makes it easier for me to plot it on a line, okay? So that's why we're here today. There's actually one more thing I'm going to do. I'm actually going to write it like this, just because I'm going to, for a moment, I'm even going to ignore the fact that theta wraps around upon itself. So just to start the discussion. Okay. So now we have a first order nonlinear differential equation. We haven't lost this troublesome sign x, the one that causes us our problems. And you're going to see why. I mean, you already have a sense physically for why, but let's see it. If we graph x versus x dot, okay? Then we can quickly learn a lot about the system. So I'll draw it for u equals 0 first, the passive case. It just looks like negative sine theta, right, basically. Where the magnitude is MGL over B to negative MGL over B. Right, this is the u equals 0 case. And what's the virtues of drawing this graph, or of making this graph, is that I can instantly see the types of things that can happen in this system. So first of all, every time it crosses the axis, that means there's some state x where x dot is 0, right? So these are fixed points, possible fixed points of the system, okay? So unlike a linear system, nonlinear systems can have multiple fixed points, and they don't have to be at the origin or anything like this. That's already sort of new, maybe. The other thing that's cool about making a plot like this, if it's a one-dimensional system, if it's just a single variable and first order, then you actually know everything that happens between the fixed points too, for all intents and purposes. You can't necessarily tell me that the way it evolves in time, but I can tell you where things are headed. If it's above the axis, that means anything that starts here is going to move that way. If it's below the axis, everything in that set of initial conditions is going to move that way. And similarly, anytime I am above or below the axis, I can immediately know what's happening in those regions. Not as a function of time, that's harder, but it's certainly the direction. So I can instantly just graphically see that, that this fixed point is special in the sense that trajectories that started, or states that started near it will now evolve in time towards it, and this is a stable fixed point. Similarly, although this is the wrapping effect that I'm ignoring here, but this system has stable fixed points over here. And these are unstable fixed points, right? So if you started exactly there, it'll stay there, but if you go even just a little bit one way or the other, it's gone, right? So what does that correspond to for the pendulum? That's the unstable fixed point, right? And this is the stable fixed point down here. Sorry, if it's overdamped, it's actually going to never oscillate. It'll just go straight down to here, okay? Good. But this is also a chance for me to give the other definitions here. So the set of initial conditions which eventually arrive at this fixed point are called the region of attraction of that fixed point. This region here, it's really just this line interval here, right? This is the region of attraction of the fixed point at the origin. And these boundaries here are called the separatrix. And they can be funky in high dimensions, but still. Is that good? People, basic definitions are okay? We have, I've written them slightly more carefully in the notes. All right, so this is cool for the pendulum. It sort of matches our intuition. It's good. But the nice thing is that this was a sine wave, right? But I could draw arbitrarily complex one-dimensional differential equations here and start asking the same type of rich questions, okay? So I put a neuron example here. Let's analyze a recurrent neural network, yeah? Now, I don't want to get you too excited. It's not a deep network. It's like the most shallow network I can possibly do. It's got a single neuron. It's one-dimensional plotting. But but we're going to understand it. And it's actually real. So how many people have heard of something called an autopsy? Yeah? Okay. He took the lecture last time. No, I can't see. All right, so autopsy is sort of the simplest example of recurrent neural networks in biology, okay? So let me just give a super basic setup for this. So how do we normally think about neural models here? Is we think about a bunch of inputs going into some system. In this class, the inputs are U. I'll go ahead and, I would like to call that B, but I'm going to call it W just because it's a neural network weight. Okay? And then I'll pass that into some nonlinearity. And then I have my output, which outputs in this class are typically Y. Okay? We'll use a couple nonlinearities in the next few minutes just to have said it. So the tanh is one of the most popular ones. Tanh has the property that it goes between -1 and 1, x, tanh of x. The other one we'll use, the standard sigmoid here, is similar, but in the domain this is my sigmoid nonlinearity, which goes from 0 to 1. Okay, another great thing about this that I'll use in a minute here is that tanh x is approximately equal to x at the origin. So the slope there is actually x. All right, so, but recurrent networks are what happens when you take the y and you feed it back around to the input, right? And so we do these in deep networks, especially for sequence learning and the like. But the autopsy is a particular special case where you have one neuron, exactly, that feeds back on itself, and there's nothing else in the network here, okay? And there's actually an open question about whether this happens in your brain. It's probably uncommon, but it actually happens a lot in experiments because people experimentally have been taking neurons out of a tissue, putting them into a chemical bath to have them sort of destroy their processes, and then nursing them back to health, and they grow into they've got no one to talk to except for themselves, so they grow out their processes and they end up connecting to themselves in a dish. So if you look in a dish after a neuron has been sort of nursed back to health, you often find single neurons that are talking to themselves only with this rich connection. And actually, so Sebastian Sung was my advisor, and just before I actually joined his lab, he wrote this paper about the computational aspects of the autopsy. And it was one of the first sort of, I think, clear descriptions, the simplest model you could think of the idea of what would short-term memory look like in the brain. We think of long-term memory as you set the weights of your neural network, of course. But what does short-term memory look like? Well, maybe it's the activation of your neurons. If you have persistent activation of your neurons, that's like how a short-term memory could be stored. And this is a model that's as simple as it gets, that's capable of persistent excitation, therefore capable of short-term memory. And we're going to see it in a plot, okay? So the model of the autopsy, where we just have a single neuron as a dynamical system, we think of it as x dot equals -x. That's some leak rate. It's a leaky neuron, plus its inputs, which in this case, sadly, it's only got itself to talk to, okay? So that's our equations of interest. And if I plot that function now, x versus x dot, this thing looks like the line of slope -1. That's easy to plot. But then if I add the tangent on top of it, then I get, this is where my colors help. Then it's still, it's the, you know, it only takes values between -1 and 1, so it's only going to move that curve so much, but it's basically that curve tilted up on its side here, so I get curves that look like this. In particular, it looks like this when w is less than 1, and it looks a little different when w is greater than 1. Okay? So what does this neuron do in terms of its activation? So we haven't actually stimulated it, but let's say it started off in some level of excitation. What is x, which is meant to correspond to a nominal firing rate, you know, in shifted units or something of the neuron? Well, if w is less than 1, it has a single fixed point here. And that fixed point, this is greater over here, and this is less. So it's actually going to be a stable fixed point at the origin. What happens if w is greater than 1? I get 2 more fixed points. I could draw this, again, I'm getting a little crowded here. These become stable fixed points, and that one becomes unstable. Okay? Three fixed points in this one. That's in the origin, sorry for my miss. Where this one is unstable, and these are stable. Okay, so this is an interesting system now with a notion of persistent memory, of short-term memory, if you will, that if it starts over here, it tends to stay over here. If it starts over here, it tends to stay over here. To make it a little bit more interesting, you could add an input. So let's say experimenter's got a probe and hits it with a little extra input, or there's someone else in the network that talks to it just for a moment here. Consider what happens if I were to send along, for instance, you know, u is 0, which is the case we've already understood, so it's found itself in one of these 2 fixed points, let's say. And now I send a pulse for some amount of time, and then I zero it again. If that pulse is long enough for any of my transients to, you know, to die out, if you think about what does adding that w do to the function tanh, it's effectively going to move this whole curve up or down. Because it's going to be like, yeah. If u is positive, it's going to be more like this. Is that right? And u is negative, it'll be like this. It's going to shift it this way. So if I'm happy with my 0 here, but if I were to, for instance, start the system in one fixed point and then pulse it in one direction, I can make it so this is the only fixed point in the system. It's a stable fixed point. the system definitely goes there. And when I let go, it's latched, right? It's like an op amp or some other, circuit that's going to latch its memory, right? In a simple neuron model. It's kind of cool. I did make a Python version of this just in case my drawing was bad. So if you were to have W being greater than 1 in this case, so I just chose W to be 2, and plot what happens for different U's, right? You can put it in one regime where it's got a single fixed point. That's like the purple line here, a fixed point here. If I now bring U back to 0 to the green, it'll stay at that fixed point. Yeah? That's a deep question. What does it mean in terms of memory? But the idea that neurons can sort of sustain activation and so they can latch, right? That's somehow finding discreteness in a mess of continuous firing rates and stuff like this. It's the simplest model of, let's say, persistent activity.
So you can activate them and then have them latch onto something else.
That's what I'm proposing here, is that you can stimulate it in one way and then let go, and it'll remember. So I'm looking at a cat, I don't know, and my cat neuron turned on, right? And then the cat went away, but I can remember the cat. That's a leap that I wasn't expecting to make, but there you go. Okay. Good, so yeah, please.
Would you need to somehow make the U pulse like continuous, or would it like jump?
So a more careful analysis, if I were to plot some, look at the dynamics of U, right? I'm saying, please forgive me that, and just make this long enough that it settles into its new equilibrium and then goes. But a more careful analysis, you're right. We should look at the rate at which it converges. But like I say, once you get into the specific time details, then the pictures aren't enough. Okay, so more famous than the AUTAPs, these days people talk about LSTM networks, long short-term memory, right? So this is short-term memory. How would you get a longer short-term memory? In fact, so I think I have a blurb here about it. Long short-term memory. This is the stuff of now deep networks, and if I want to do a recurrent network, this is what you did last year. And if you're now you're doing transformer networks or something different, but still, there's some applications where people are still using LSTMs. They were originally designed as a way to fight some of the numerical problems people had in neural networks, training sequence learning, where they would have vanishing gradients and the like. None of that is the topic for today, but just these are actually used in real deep neural networks, okay? And because we can plot arbitrary functions, and this one is completely arbitrary by my book, but we can actually figure out a little bit more about what an LSTM does using our graphical analysis, okay? So let's write at least the one. There's a million variants of LSTMs out there. The intuition is sort of the same, is that we'd like to have a latching persistent network. It should be differentiable for neural network training procedures. Okay, and it turns out that walk through the needed recurrent unit variety, then it looks not so different, actually. It's negative x. And then, okay, times tanh of now just B U3 plus C. Okay, that's what it is. That's what I get when I muck through all the stuff and try to write it in a single line. This roughly here corresponds to a forgetting gate. This term here corresponds to an input gate. This is only just if you have seen LSTMs and you want to make that connection. It's not core underactuated material here. And this is sort of the input being shoved through a tangent nonlinearity. Okay. If you ask me why, I feel like this is, this is what you get if you're curve fitting with differentiable things and you just throw a bunch of, stuff together and the fact that it works better than other things is, I have no idea why, but it's still just one function of a single variable. It's got a lot of different parameters. That's the one thing I can't do a parameter sweep of all the different coefficients very nicely for you. But for any set of weights, we can understand its dynamics with graphical analysis, right? Although it's a little hokey. Okay, so if I've turned everything off, basically, if I'm understimulating the forget gate and the input gate or whatever, then actually this system looks like that, which in the sensible parameter regime, it basically looks like a stable linear system that tries to go back to 0. Okay, so if the inputs are all, they're actually, because of the way it is, they have to be negative, then the system tries to just go back to 0. This is the forgetting, okay? If you now start stimulating it, if you, for instance, turn off the forgetting, then you get something different. Sorry, it's a little busy here, but that blue line is basically what we just saw a minute ago. And as I turn off the forgetting input, I get something that looks more and more like a curve that looks like this. It goes down and then it goes flat along the line there. So what does that do? Right, it's marginally stable. That's one way to say it. So people say it remembers whatever it's had, whatever's in its current memory, it just stays. It's x dot equals 0 most of the time. It's unstable. If you were to knock it, it moves. But it's roughly x dot equals 0 over here, and if x was too low, it gets pushed that way. Okay, that's sort of reasonable. And then if I were to start giving it some input, then actually it's an integrator, effectively, of the input. So it comes out with, these are a handful of different input values. Depending on that input value, it just integrates the input value. So that's unstable, actually. If you were to turn it on, it's just going to grow and grow and grow and grow. And that's what it does. And it's actually kind of a pain to try to analyze because of that. All right? So if you start exploring the parameter space, you'll see it does weird things. And I really, it's crazy to me that that's the tool of choice. But there you go. Ooh. Okay, any questions about that? Are you sold on the merits of graphical analysis? You can understand shallow neural networks, right? There's a couple more points I can make that they come up again and again in our systems. So one of them is that, and we kind of saw it we saw it already here, but as I changed the input in one case, the fixed points moved, right? In fact, the number of fixed points moved, right? Even in this example, or in the pendulum, for instance, if I were to start now applying this was my u equals 0. But if you remember my equations, crap. Oh, it's right there, see? Bx dot equals u minus, so there's a, u just adds in linearly, okay? So what happens if I start changing u? It's just going to move that curve up and down, right? So the fixed points are going to move in response to a constant torque, right? In fact, these two start coming together. They still, this one's still stable and this one's unstable. So what does that correspond to physically? If I start applying a constant torque, my pendulum's going to try to hang out over here where the torque is fighting gravity. But the unstable fixed point moved too, right? It's not up here anymore. It's not even over there. It's actually over here because the torque, that same torque I'm applying here, is fighting gravity right there. That's where the unstable fixed point is. Okay? Now, if I keep moving it up, something dramatic happens, and that's actually how I hit a tree with the pendulum. I was in an early version of the Underactuated class. I had a physical robot here. I said, look, if I turn u up too high, it'll go unstable. I said the words. The robot will go unstable. And it was supposed to be bolted to the table, and it was supposed to have a velocity limit. I threw the pendulum right across the room. It ripped its wires out of the thing. But I think the lesson was learned by me, for sure. Anyways, if you go up too high, the system becomes unstable, and will just go that way forever, really fast in a dangerous way. Okay, so it's cool. Nonlinear systems can change even their number type of fixed points. We're going to have you draw a bifurcation diagram, which is just a simple plot, but maybe I'm going to skip drawing a simple version of it here. But in your homework, you can make a plot of, as I change a parameter, where do the fixed points go? And it's a beautiful way to think about nonlinear systems. Okay? Good. So, yeah, I'll skip it. I want to get to 2D systems before we get too far. So, the graphical analysis still works for two-dimensional systems. Plotting is still super useful, but it's not as, this one I know everything that happens by looking if it's above or below the curve. It gets a little bit more subtle in 2D, okay? So I'm going to go back to my my normal pendulum in 2 degrees of freedom here, or in acceleration. I removed the assumption that b was very large. I can still make a plot. And this is super important, and some of you have done this often, and some of you that I just have to make sure we're all doing it the same way here. But I can make a plot of this where the input is my position and velocity. It's a phase portrait if you haven't seen it, right? But my input is theta and theta dot. And so that corresponds to now a plot, again with theta and theta dot here. At every point theta dot, I'd like to draw a vector which corresponds to the derivative of this, right? So at every xy position here, I've got two numbers I want to plot, so I'm going to draw it as a vector. Okay? And if I do that for the pendulum, I can start looking, if theta equals 0, that's a pretty easy case. What happens if theta equals 0? I'm sorry, I pointed to theta dot equals 0 and I said theta equals 0. Let's do when theta dot equals 0 and look along this axis. When theta dot equals 0, then theta dot is always going to be 0, so my x component of my vector is going to be 0. So the arrows here are going to only go up and down. And theta double dot is just going to look like sine theta. So let me say that with a picture here. That makes sense? So every one of these points, in this case, the x component is theta dot of the vector, which was 0. This one is my acceleration. And that's just my sine wave, but now we're plotting it as a vector in a higher dimensional space. The other easy case is when theta equals 0. This term disappears, and I just get b. So if I move along here, so I've got I've got theta equals 0. This term is 0. Theta dot is whatever theta dot is. And theta double dot is proportional here. So I just get something that looks like this. And the reason it's useful to draw those vectors is because the solutions of the system, if I start at any initial point, are a trajectory that just follows those vectors around state space. Those vectors tell me where things are going to move, and in particular, if they start here, this is my, I forgot to say this is my b equals 0 case. It's the simplest case where I get a perfect orbit around the system. And over here, it repeats again. They're pretty circular near the origin, and they're a little bit elongated into an eyeball kind of shape over here. And these are the trajectories now of the, in this case, undamped b equals 0. These are the trajectories or orbits of the undamped pendulum. What happens up here? If I start my system up here, yeah, good. That's what I did in class, I guess. Something like that. All right, and similarly over here, these are all going this way. It's all going this way. Okay, so the pictures get a little bit more complicated, but they're still super useful in 2D. If I were to add damping now back, then my theta double dot term, which was 0 here, becomes a little bit negative here in this case. So damping pushes this thing down a little bit. And the damped pendulum has orbits, you won't be surprised, that will circle around and go like this, yeah? And something that started outside the eyeball can actually go like this, end up in an orbit over here. Okay, we can, it's still a little bit, it's still possible, although a little bit less nice, to look at the fixed points here. So a fixed point of this system is going to only occur when theta dot equals 0. It can only live on this axis. This is one fixed point. This is another fixed point. And so the question I have for you, I think we're willing to say that this fixed point is unstable. But the question I have for you here is this fixed point stable? It's not attractive, but it doesn't run away, right? And this is the important point here, is that there are many definitions of stability, well, for nonlinear systems. That stability is a more subtle concept, okay? There are levels of stability. And that's the last set of definitions I want to give you today. Fixed point x star is locally stable. I'll put it like this here first. When we say stable, if we're being extra careful, we'll say in the sense of Lyapunov. I will write ISL. But actually, if we just say stable, we mean stable in the sense of Lyapunov. And the picture here, yeah?
What is the sense of Lyapunov?
That's why I'm going to give you the definition. Coming right now. I'm glad you asked. If for every epsilon greater than 0 but small, there exists a delta greater than 0. X0 minus X star is less than delta implies for all t, x of t minus X star is less than epsilon. Sorry to hit you with the most obtuse one first, but I think we can parse it pretty well. This says this is some distance metric. You pick your norm. If my initial conditions are some distance from my initial okay, let's think about it this way first. I would like to certify that for any epsilon, this defines some ball of states, right? This says I'm going to consider all states that are inside some region. If here's my fixed point, I'm going to be able to draw any epsilon ball. I'm going to call the system stable as if I give you epsilon, you need to come up with a delta, which should be smaller than epsilon for this to work, such that if you start inside the small ball, you'll never leave the big ball. So it's about not going away too much, right? Okay, so I give you, the game is I give you epsilon, you pick a delta, such that this condition is true. I started here. For the rest of time, I'll stay inside there. So that's a useful definition for this case. This one, as I've tried to draw in multicolors, this is stable in the sense of Lyapunov, but it might not be stable in all the other definitions we're about to throw at it. Yeah?
This definition, could you enter a stable orbit inside of the big ball?
Absolutely.
And the fixed point in the middle of that would be...
In fact, these are not stable orbits, but these are going to be in orbits. All the solutions are orbits. Right? Now the trick is if you actually have a stable orbit, it might be that this would break because I have to be able to satisfy this for any epsilon. Right? So it's subtle, but you see what I mean? If you let's say there was a stable orbit that was 1 centimeter from the goal, right? Then that means if I picked half a centimeter, it's going to go out. All right. So. Stable in the sense of Lyapunov is, when we say stable, we're going to mean stable in the sense of Lyapunov. There are more definitions here, though. It's attractive if it actually gets to the goal. If, as the limit of time goes to infinity, x of t goes to x star. So if it actually gets there, it's attractive. It's asymptotically stable if it's stable and attractive. Now, if you're really thinking about this right now, I hope you're thinking, how could I possibly have a system that gets to the fixed point as time goes to infinity, but somehow isn't stable in the sense of the Lyapunov? Why do I need this extra?
Because it could go outside the ball and then back.
But those things are at odds. You have to, I mean, it is true. Of course it is true that it's possible to construct systems where even though you will eventually get to the goal, you can go arbitrarily far from the goal on your path to the goal. And we're gonna ask you, but there's one in the notes and there's one in the homework, okay? But those are actually separate things. And then the last definition we'll use is exponentially stable. If it approaches the goal, the fixed point, at some rate, okay? If x0 is just some perturbation away from the original, then I'd like to say that for all t, the distance between x of t and my fixed point is bounded by some e to the negative alpha t. Okay, so this says not only that I'm going to get there, but I'm going to get there at some rate. What do linear systems do? Oh yeah, please.
If x star and x0 are kind of in multidimensional points, then what does it mean for x0 to equal x star and so on?
Yep. So think of this as epsilon plus the, this is a vector in the same space. I am sorry to use the same let me call it, epsilon times some random vector here, but I want that in a vector epsilon. I'll do that. Good call. Yes?
Does exponentially stable correspond to having a stable linearization at the fixed point?
Awesome. So linear systems are, if they're stable, are exponentially stable. Exactly right. So yes, what you said is true. In fact, if in the x versus x dot case, where we can plot everything, linear systems can only look like this, right? Or they look like a line here. If I have x dot equals a of x, let's say. If a is positive or negative, it might be a positive line or a negative line, okay? This system converges exponentially. The solution is actually the exponential towards this. And even in the multidimensional case, yes, it's true, but here in this case, what this says is that whatever curve I've got, its approach to the origin is bounded by some linear system. Good.
So does the value of capital C and alpha
Depend on.
function allowed to be an arbitrary function of the epsilon vector, or is it fixed for all epsilon?
No, you're right. It's a function of the. So for any initial condition, I can bound that. I can find a C and an alpha that bounds it. Yeah, and C will change in particular. Yeah. For a linear system. Good. Questions are good. So And then finally, we're going to say it's unstable if it's not stable ISL. So it's worth thinking through yourself. It's non-trivial, but if you have asymptotic, well, sorry, this one's trivial because we've assumed it, but asymptotic stability guarantees stability in this sense. Exponential stability implies asymptotic stability as well as, therefore, stability. So this is a strict hierarchy once we impose this if stable and attractive in the middle, okay? So if we were to just say stable or just say unstable, we're going to use this as our base, okay? Now the crazy thing is that nonlinear systems can do all sorts of different things like that. So they can have multiple fixed points. That's already new. Linear systems don't do that. Linear systems are always either stable at the origin, unstable at the origin, or marginally stable at the origin. We've seen examples of nonlinear systems that have multiple fixed points that move with parameters and the like. They can do other things too. They can have finite time escape, right? So you can actually blow up in finite time, right? So they go to infinity very fast. But you can also have finite time convergence. A linear system takes an exponential amount of time to get to, it'll only get exponentially close to the origin, right? It's sort of in any finite amount of time, it will not actually get to the origin. But a nonlinear system can get to an origin in finite time, okay? So there's a bunch of cool things that systems do. So and these aren't arbitrary. They sort of, it feels arbitrary when I'm just throwing definitions at you, a wall of definitions, but they matter. Like, we're gonna write programs for systems that try to prove stability of complex systems, of walking robots and the like, okay? For a walking robot that has a frictional contact with the ground, you'll be able to find a certificate of stability in the sense of Lyapunov, but you're not gonna be able to find a stability certificate that's asymptotic stability or exponential stability. Friction is gonna prevent that, okay? If you write a program that requires this for it to be satisfied, you will fail, or you'll fail to certify that program. I'm not saying you're gonna fail the class, right? So they matter. Like the definitions imply different computations, yeah?
Sorry, can you repeat what you said about not getting to the origin finite time?
I said a linear system which has a solution of the form e to the a t. It will, if you look at any t, it's not actually at 0. You started an initial condition off the origin. At time 263, it's not at the origin yet. It's getting closer, right? But if a nonlinear system can actually arrive. So can discrete time systems can arrive in finite time. Okay, so they actually matter. This is good. Any other questions? I skipped one part and then ended up early, but I did promise a quick announcement here at the end of the class. So come on down, or if you want to stay from there, whatever you want to do. Yeah, totally.